In this lesson, we're going to be looking at modeling with linear equations, and normally that means modeling from a word problem. So when we talk about modeling with an equation, what we're basically saying is, how can I read a situation or read a problem and make all of the definitions required in order to declare variables, and then also in order to create equations that will allow me to do the algebra from that point forward and actually solve the problem or come up with an answer to a question. So that's what we're going to be focusing on in this lesson. Some steps to keep in mind as we go through some examples. We want to identify our unknowns and declare them as variables. I'm going to specifically try to model this last part, which is some trial and error. So I'm going to be explaining to you some of the ways you might think about these things, and I don't want you to be afraid to take a step back and maybe even rewind a little bit, decide, no, that's not working. That's part of the problem solving process, is to refine it. And sometimes that means you have to kind of go back to where you started, throw some things away, and approach it in a new way. You're not always going to get it right the first time through. In order to solve a system of equations, we actually need two equations. So when you're doing this work, if you can't come up with two different equations, maybe you do need to go back to the drawing board and start over again, reconsider how you've approached this. Solve using the method of your choice. Saying that, in general, you're going to want to develop algebraic methods rather than graphical. Sometimes the solving by graphing can work wonderfully, but most of the time you're going to be looking at solving by substitution or by elimination. And then finally, make sure that you write a concluding statement that answers the original question. That means going back and rereading the original question, making sure that you actually know what's being asked from the word problem. So, without any more preamble, let's go on to our first example. This one's a fairly simple one to begin. In all of these examples, for the sake of time, I'm not going to solve these, and I would suggest when you're first learning how to model equations, you're going to focus on just coming up with your variables and the equations themselves. You'll get plenty of practice solving equations, and later on in the course, in this unit, we're going to actually also do modeling plus solving. So let's focus on modeling just for this lesson. So let's pick out some of the key features in this sentence. So the sum of two numbers, so I know I'm going to be adding two things together. And it's two numbers, so that gives me a pretty big hint about my variables. We've got a difference, and that means I'm of course going to be subtracting. So they give me a sum of 72, and they give me a difference of 48, and I'm trying to find the numbers. So it's pretty clear here that I'm trying to find two numbers, so I'm going to let x and y be the numbers. So I should always be starting a problem with something like that, with some sort of identification of what x and y stand for. So in this case, the sum of those two numbers is 72. So my first equation is that x plus y is equal to 72. And the difference in those numbers is 48. X minus y is equal to 48. Or y minus x equals 48. It doesn't actually matter which one of these two equations you choose, meaning it doesn't really matter which order you do the subtraction. Sometimes it does matter, but in this case, it just means that the answer you get, what you call x and what you call y, if you did it using this first equation, and let's say that a friend of yours did it using this second equation, you would both still get the same answer, but what one of you is calling x, the other person would be calling y. And what one of you is calling y, the other person would be calling x. But you would actually agree on what both of those two numbers were. And then once you get through all of that and solve, don't forget to go back. It says to find the numbers, so you would finish off with a therefore concluding statement, therefore the numbers are, and you would fill that in based on the results of your solving the system. Okay, now we've got Bert earns an hourly wage plus tips. So an hourly wage plus tips, you can probably relate to this. This is pretty standard for someone working in the service industry. 1 week he worked 12 hours and he made a total of $117. So that would mean that his wage plus his tips in the first week was $117. In the next week, he worked 10 hours and he earned the same amount of tips as the week before, and he earned a total of 110. What is Bert's hourly wage? Well, that's an important part. This isn't always the case, but when a question is asking you for a specific value, quite often that is going to be one of your variables. And in this case, it is going to be one of our variables as well. Now, first thing I'm going to say is I'm going to say let H represent hourly wage. And I'm doing this on purpose. I actually don't want to use H, but I want to point out something to you, which is if I look back through the question, you can see it refers to 12H as in 12 hours, 10H, 10 hours. So maybe H isn't the best choice here. It's not terrible, but maybe I'm going to, instead of saying H, I'm going to say let W represent the hourly wage. And that's just as good. There's no problem with that. So the hourly wage gets multiplied by the number of hours that he works. And these things give a total of 117. The other thing that gets added in there is tips. So that's going to become my other variable. So I'm going to let T represent tips. And now that I know the hourly wage and now that I know T, let's take a look at week 1. Let's form an equation for week number 1. In week number 1, he worked 12 hours. So if he worked 12 hours, how much money did he make from working those 12 hours? Well, he makes W dollars per hour. That's his hourly wage. And so if he worked 12 hours, he would make 12W. And he also makes tips. So his 12 hours plus his tips must be equal to, in this case, it's 117. When you're doing problems, I really recommend that you don't bother with units. Remember that there are units, there are things like hours, there are things like dollars, but we're going to reintroduce those units a little bit later on in our concluding statement. It just provides clutter in our actual equations. And that would be our first equation if we're solving a system of equations. In week 2, in week 2 he worked 10 hours, and so that's going to be 10 multiplied by W, plus, and it says he earned the same amount in tips. So earning the same amount in tips means he once again earned T in tips, and this time it was for a total of $110. That's week 2. And if you've been keeping up on our other lessons, or if you remember our other lessons, you can see I've got a 1T and a 1T here. So this system is actually ideally set up to do elimination. And as I said at the beginning, I'm not going to do that, but I'm giving you, you can go ahead and solve that if you want to, but the purpose of today's lesson is to focus on the formation of these equations and identifying and declaring our variables. And then we would solve this and we would go back and give a concluding statement on what is Bert's hourly wage, and that is our W. So we need to solve for the variable W here. We don't actually have to solve for the variable T. That's an important thing to note here. We're only interested in W. So sometimes this will happen in a problem, so make sure you're reading the problem very carefully. You can do the extra work, you can find T, but you're not going to get any extra credit for doing it. The important thing here is to find what is the value for W. And moving on to our next example. Okay, you can see that I've got a blue background in this one, and that's because I'm actually going to show you this one 2 different ways. I'm going to just talk about this one to start, and then I'm going to show you a slightly more organized way to do it. So now we've got Bert's friend Ernie, who's driving at a speed of 50 kilometers per hour from Toronto to Kingston. And then from Kingston to Ottawa, he drove at 80 kilometers per hour. So we've got two parts of a trip going at two different speeds. The whole trip was a distance of 550, and it, meaning the whole trip, took 8 hours. So these two numbers, 550 kilometers and 8 hours, they represent totals. So there's a good guess is that these are not the things that we're going to be representing with variables. We want to know what is the distance from Ottawa to Kingston. So again, a little hint there. If the distance from Ottawa to Kingston is one of the things we want to know, and part of the trip was also from Toronto to Kingston, Kingston to Ottawa is the same as Ottawa to Kingston, so part of the trip was from Toronto to Kingston, and part of the trip was from Kingston to Ottawa, and we're interested in the Ottawa to Kingston part. That's the same as this part right here. So this seems to indicate to me that I can let x be the distance from Ottawa to Kingston. And in that case, the other distance that I'm interested in is going to be let y be the distance from, in this case, that will be from Toronto to Kingston. And if I were to add those two things together, that's the total distance, and that's what they say here. The whole trip was 550 kilometers. So that comes out right away. I end up with x plus y is equal to 550 kilometers. There's my first equation. The second equation is not so simple, and that's because it requires a bit of an analysis of how do these quantities relate to each other. We've got some speeds, 80 kilometers per hour. We've got a time here, hours. We've got distances. So how are these things going to relate to each other? And that's what becomes the difficult part. The first thing you need for this is the idea. I'll start with the equation. Distance is equal to speed times time. That's one way to think of it. Or another way, and this is maybe a way for people to remember, whenever you're dealing with a speed, that's 50 kilometers per hour. Okay, that's one of the speeds that's given to us here. So that's a speed. Actually, let's go ahead and call that one V1. But 50 kilometers per hour, what is 50 kilometers? That's a distance. And what is per hour? That's a time. So this together might help remind you that speed is equal to distance over time. So both of these mean the exact same thing. D equals Vt is just another form of V equals D over T. And there's actually a third form from this. If I start with this one, D equals Vt, and I divide both sides by V, you'll see that the V's divide out here, and I end up with T equals D over V. So depending on what we're working with here, we may want an equation in terms of D, an equation in terms of V, an equation in terms of T. We formed our first equation making use of this quantity, a total distance of 550. The other total that we have is a time. So that makes me think that I'm going to want to write my second equation in terms of time. Sorry, I didn't mean to do that. I meant to extend the page. And so that gives me a bit of a hint that I want to write that T1 plus T2 is equal to 8 hours. I've lost my pen. There we go. T1 plus T2 is equal to 8 hours. Now this is quite a bit more sophisticated a problem than the first one we did. T1 is equal to D1 over V1. T2 is equal to D2 over V2. And that's equal to 8. And we're almost there. Bear with me. What is the first distance? That would be the distance from Toronto to Kingston, which in our equation, the first distance of this trip is represented by the variable y. So this becomes y. And what was the speed from Toronto to Kingston? The speed of Toronto to Kingston was 50. So this becomes y over 50. Plus d2 is the distance from Kingston to Ottawa. That's x. You have to be really careful with how you've declared your variables here. And if you remember from the question, that one was completed at 80, and that works out to be equal to 8. And that's my second equation right there. That was a much more involved, a much more long and drawn out process in order to get my two equations. The first equation was almost trivial. The second equation took quite a bit of thinking, and you might not be too happy with what I've had to do there. So instead, let me show you an alternate way to approach this, which is using a table to help us organize things. And I really find this to be useful, especially for people who are new to this idea. So we've got the same problem here. Ernie drove at a speed of 50 kilometers per hour from Toronto to Kingston. Well, here's Toronto to Kingston. That's trip 1. And let's see, what are we told? A speed of 50 kilometers per hour. Drove from Kingston to Ottawa. He drove that at 80 kilometers per hour. Okay. So now we take a look at some things. Distances, we were told a total of 550 kilometers. And times, we were told a total of 8 hours. And it makes sense to add up distances. For each part of the trip, you add up the distances, you get a total. For each part of the trip, you add up the times, you get a total. For each part of the trip, it doesn't make sense. If you drove the first part at 50 and the second part at 80, you didn't drive the whole thing at 130. So this box in our table actually, almost always, not always, there are some exceptions, but it usually gets X'd out. So now we can start to work in terms of distances or in terms of time. Now it's up to you. Since the question wants to know what is the distance from Ottawa to Kingston, if you write these out as dVt, just remember the letters in that direction, distance equals speed times time. So the headings, if you've written it out correctly, they get written out in the same way as the equation. So the distance from Ottawa to Kingston is what we want to know. So that's the same as the distance from Kingston to Ottawa. So that's what we want to know. I'm going to call that one x. I'm going to call this one y. So how do we write this? Well, we have to go back to what I was saying before, which is that you can rearrange this as time is equal to distance divided by speed. And so time is equal to distance divided by speed, distance divided by speed. And so from this, we actually get our two equations. This one, the distances add up to 550. Y plus x equals 550. And this one, the times add up to, just get rid of this, y over 50 plus x over, sorry, I made a mistake here. This is supposed to say 80, not 50. Plus x over 80 is equal to 8. So there we go. And then in solving this, there's equation 1, there's equation 2. To solve this one, you don't want to be dealing with these fractions, so we're going to have to multiply everything by a common denominator for 50 and for 80. I'll tell you right now that common denominator, in case you decide you do want to try this yourself, the lowest common denominator here is equal to 400. So we're going to multiply both of these by 400, and then that will get rid of our fractions and give us our second equation in a much nicer form. And finally, we've got a mixing type question. We've got a lawn fertilizer, which is made up of 24% nitrogen, and another lawn fertilizer is made up of 12% nitrogen. How much of each fertilizer should be mixed? So we want to take these two bags of different types of fertilizer, and we want to end up with 100 kilograms. So let's say we essentially have an unlimited amount of the 24% fertilizer. We have an unlimited amount of the 12% fertilizer, and we're trying to produce 100 kilograms of 21% fertilizer, 21% nitrogen fertilizer. So this is the easy part. I'm trying to make 100 kilograms, and I'm going to use a certain mass of the first fertilizer and a certain mass of the second fertilizer. So that one seems pretty clear. I'm going to let X represent the mass, and it's important to put these things in here. You might even say in kilograms of 24%, and let Y represent the mass in kilograms of 12%. So those are the two fertilizers I'm going to mix together, and X plus Y has to be equal to 100 kilograms. That's what we got from this. Now let's look at the amounts of nitrogen that are in there. Well, if I have 24% fertilizer, that's X. I have X kilograms of that. Then that means that it's going to contribute, for every kilogram of this type of fertilizer, I'm going to contribute 24% nitrogen. For every kilogram of the 12%, I'm going to contribute 12% nitrogen. So we end up with an equation. We're trying to create a 21% mixture, and this gets a little tricky. So I'm going to show you the mistaken equation, and it's understandable why you'd make this mistake. I'm going to create 24, and as I mentioned before, a lot of times we don't want to carry extra clutter here. I'm actually going to show you this a few ways. 24 times the X mass plus 12 times the Y mass is going to be equal to 21. That would be, this is done. This one is actually correct. This is wrong. So take a look at this and try to figure out why this is wrong. I've got 24% mixture multiplied by the mass of the first mixture plus 24%, plus 12% of the mixture times the mass of the second mixture is equal to 21%. And obviously the thing that's missing there is how much of the 21% mixture. I've got a percentage times a percentage times a mass, so I need a percentage times a mass. And so for this one, I also need to include 100. So this one is a percent times a mass, a percent times a mass, a percent times a mass. Okay. Another way we could have written this equation, it's still legitimate, or you might get sticky about this and say, well, hold on, no, it's percentages. That's not right. 24% is not the same as the number 24, and it's not. I'm just trying to make these equations easy to work with. But if you notice that, then good for you. The way you might have started this is 0.24 times X plus 0.12 times Y is equal to 0.21 times 100. Because now we've actually converted these to percentages. These are proper percentages. What have I done between these two? If I multiply this entire bottom equation by 100, 0.24 turns into 24, 0.12 turns into 12, 0.21 turns into 21. And we've learned in a previous lesson that you can multiply an equation, so long as you multiply everything or divide everything by the same amount, so long as whatever you do to the left side, you do to the right side, that's mathematically valid. So that's another option. That's another way that you could approach this. And I think I mentioned I was going to do this a third way, but I don't think I need to now. I think that that's perfectly fine. So it could be either of these. in order for you to solve this. Okay, and I believe that's it. That's it for my 3 examples on modeling. And I've just got my homework, and for those of you doing the homework, stressing you're not solving these questions. You're going to solve these at another time. Focus on modeling, coming up with the equations.